AP Chemistry students. This is Chapter 5, our gas law work, and I'm going to try to make a video with all of the learning objectives in it together. And so we'll see here how that goes, and then in the description section I'll leave some time markers so you can identify when each learning objective starts. Start off with the first one, the properties of gases in the kinetic molecular theory. And so these are the four characteristics of gases that we're going to look at. We have low density, that they're miscible, compressible, and fills the container that they're in. So low density here, the gas molecules are very far apart from each other, and therefore the density is going to be very low. And it's low, so low that we measure the density in grams per liter. When solids and liquids, we measure the density in grams per milliliter. They're miscible. This means that they mix together in homogeneous solutions. So regardless of the gas, no matter what you have, they're always going to mix together in a homogeneous way. So, for example, if you think about air, it's primarily nitrogen and oxygen with some other trace gases in it. They all mix together to form this homogeneous mixture or homogeneous solution of air. They're compressible, and if you think about gas molecules being very far apart from each other, that means that they can be squeezed back together so that they're more close together. And eventually, if you squeeze them enough, they're going to turn into a liquid, and then further on you can maybe possibly even get them into a solid. A good example of this would be liquid propane, because most of us are familiar with LP. That's the stuff that we use to grill our food with on an outdoor grill. If you don't use charcoal, you use LP, and it's liquid because of the pressure that it's under. And then when you release that pressure and turn it into a gas as it goes into the grill, that pressure is released, and so the density goes down and it goes back into a gaseous form. So highly compressible and can be compressed into a liquid. It fills a container that it's in. This can also be said that it has an indefinite shape and indefinite volume. So that's different than liquids and solids that both have definite volumes. And so this one doesn't have either shape or volume. It fills the container that it's in completely. All right, what causes gas pressure? Well, pressure is a measure of force per the unit of area. Now, the force that's being exerted in gas pressure is the collisions of the gas particles with the walls of the container that it's in. And so if we think about any kind of surface or any kind of wall of a container that would be able to feel this pressure, that's what's causing that air pressure. And we have a certain amount of air pressure that we live in right now because of the mass of air above us. It's pushing down on us. The gravity keeps our atmosphere to the earth, and that air then has mass and it pushes down on us, and so there's a certain amount of air pressure on us all the time, and that's approximately what we call 1 atmosphere. And we'll talk a little bit more about how pressure is measured and why that's important maybe later on. All right. The next one here we've talked about some already, but let's go ahead and make sure that we reiterate some things. Why is the density of gases much lower than liquids or solids? And this is because of how far away those gas molecules are from each other. Where liquids and solids, they're much, much closer. And because they're so far apart, again, we measure in grams per liter. All right, I'm going to scoot up here for the next one because the next one's an important one. These are the postulates of the kinetic molecular theory. Now, there's a key word here that you may not know, and that is the term postulates. Postulate is an assumption. It is an observation, something that we say is a true statement so that we can apply it to other concepts and use it that way. So we have the kinetic molecular theory of gases, kinetic meaning motion, molecule meaning molecules, and then we have gases specifically. There are kinetic molecular theories that we can talk about for liquids and for solids. Now, as far as the gases go, we have 4 different postulates. They're in your book on page 203. I'll go through them and summarize them and do some extra explanations. So the first one is going to be that gas particles have no volume. Now again, if we think about molecules in general, they're super, super tiny things. And in the case of gases, those things are very, very far away apart from each other. Since they're so far apart from each other, the volume that we would see in comparison is so small for the molecule compared to how far away it is to the next gas molecule that we say that the particles themselves occupy no volume. So really what we're saying here is that gas particles are super, super tiny, and most of the space around them is just empty. There's just nothing in it at all, and so much so that the gas particles have no volume. All right. Next one is that they are always in motion. This motion is always straight line, it's always random, and it's always happening. And so a really important concept here is that as long as there is a temperature, those gas molecules are moving. All right, the next one, there are no attractive forces or repulsive forces. So they don't attract to each other, they don't repel each other. And so that's a pretty important one that we're going to come back to. One that's not in the book that I'm going to put on here is that the collisions are perfectly elastic. This means that when gas particles collide with either each other or the walls of the container or something like that, that they don't lose any of their energy. They don't gain any energy, but they don't lose any either. If they did, incidentally, the temperature of a specific area would start to cool down. And since that doesn't happen, we say that they're perfectly elastic. Other collisions are inelastic, meaning that some of the energy is put into something else, work or lost to surroundings as heat or something like that. If you think about like a bouncy ball being dropped to the ground, that bouncy ball is not going to come back up to where it started. That's because it lost or it transferred some of that energy to the surroundings as either heat or sound or other types of things, where gas particles don't have that. All right, and the last one is that the kinetic energy is proportional to the temperature of the gas. So what this means is that if we look at kinetic energy and we increase that kinetic energy, it means that we're also increasing the temperature, and the speed of the gas molecules are also increasing. So really, we don't increase the kinetic energy. What we do is we increase the temperature. As we increase the temperature, the gas molecules move more quickly, and since they're moving more quickly, we say that the kinetic energy is also going on. And conversely, we could say as you decrease them, the opposite is true. And this is all related to this equation. Kinetic energy is equal to 1/2 mass times velocity squared. And so we have this equation here that's related to kinetic energy, and the kinetic energy, which is directly related to temperature. Increased temperature, kinetic energy increases. Now we can also talk about the size of the gas molecules because we have this mass component. So let's say we're going to keep the kinetic energy the same. We're not going to change the kinetic energy, but we're going to then increase the mass of a gas molecule. If we do that, we have to decrease the velocity, and that keeps the kinetic energy constant. Or we could do the opposite. Let's do green. Decrease the mass, the velocity would have to increase. Now think about it in terms of vehicles and car crashes. If we were to take a large semi and try to break through a wall with it, a cement wall, it wouldn't have to be traveling very quickly to do that. So the kinetic energy is the motion needed to break through the wall. The velocity would be very slow. But if we were to take a smart car, you know, those 300-pound little cars, and slammed into that wall, to break through that spent wall, it'd have to be going much, much more quickly. So that is how those things are related. Now, one of the things that we should talk about right now is that these postulates of the kinetic molecular theory of gases are for ideal gases. And these are fictional gases that don't actually exist. And real gases then don't follow these postulates to say it'd be a law or something like that. It's close enough, is what we say. So the question that we always get then is, if this is for an ideal gas is a fictional thing that doesn't really exist, well, why do we use them? And that's because the deviation from an ideal gas is so small from a real gas that we can still use these for real gases. And we'll do some work later on to kind of prove that. But it is important. Gas molecules do have volume, for sure. They are particles of matter, and matter has mass, and mass has volume, so there's that. They are in motion forever, that's fine, constant motion. They do have attractive forces and sometimes repulsive forces, and a really easy one to think about here is water vapor. So water has that attractive force between them, which allows it to condense into clouds and then rain. And if this didn't happen, rain wouldn't happen, we would all die. That would be bad. So it's important to note that there are these attractive forces. And finally, the collisions are perfectly elastic. Also not always true. Energy gets transferred. And then what ends up happening is, if you don't provide additional energy, the container actually would cool down over time. And then it would slowly cool down and then stop moving. The gas molecules would. Now that would have to be done in like space or something like that over time, because there's always energy being inputted just because it's in a warm environment. All right. So anyway, those are the postulates of the kinetic molecular theory. A lot of information here. Make sure that you understand what's going on here and are able to apply it. And we'll look at a couple pieces down here to apply that. And let's see here. This one is going to be an ideal gas versus a real gas. So we want to figure out, in what ways can we make that gas be closest to an ideal gas. We have these four different things. We have high temperature, low pressure, high temperature, high pressure, low temperature, high pressure, low temperature, low pressure. We're looking for the answer here that means that these things will be the most true. And what happens is this one here, a big one here, is the attractive forces and also the collisions. We want to keep those collisions from happening and also show no volume. So if we think about it here, if we have a circumstance where we have high temperature and low pressure, those gas molecules are going to be moving very, very quickly. So they aren't going to have time to attract to each other. And if they have very low pressures, that means that the gas molecules are going to be very, very far away from each other. So no volume. And they're always going to be moving. So the other one is high temperature here, that they're always going to be moving very, very quickly. So constant motion. And the collisions we don't really talk about in this case. But this is the correct answer because it makes these statements most true. High temperature, no time for the gas molecules to attract to each other, and then very little volume because of that low pressure. And if we think about, again, that liquid propane example again, we could get that to happen. We could condense that into a liquid by either increasing the pressure, which is what happens there, or we could also lower the temperature. And obviously that's not really an option because we use these things for like our grills and homes to heat and stuff like that. All right. How does the kinetic molecular theory of gases relate to whether a reaction occurs or not? And you're going to discuss molecular speed and collision frequency. I'll talk about stuff here, but I'm not going to write a whole lot of notes. Let's say that we have two gas molecules, A and B. And A plus B reacts to form C. So we have these gas molecules flying towards there, and these gas molecules flying this way. And these guys are going to collide with each other. When they collide, there's some extra part here we're going to get into later on in a different chapter, but when they collide, they can make gas particle C. Well, in order for these things to be able to actually react together, we have to have a large enough velocity where they can overcome their electron clouds and merge together and form that new chemical compound. So we have to have them moving very quickly to be able to happen. Also, if the velocity is high, then we're going to get more collisions. More collisions means that we're going to have a greater chance of those being able to hit each other and form the new gas molecule. So in order to increase the rate of reactions for gas molecules, we often will increase the temperature. If we increase the temperature, we increase the velocity of the gas molecules. If the gas molecules are more quickly, we're going to get more collisions, and also we're going to get collisions that provide the product that we need. All right. Learning objective 2. So these are our gas laws. Now we actually get into some of the math. Now before we can get into some of these gas laws, we need to talk about some of the units that we can measure things in. So we are going to be using pressure, volume, number of moles, temperature. So those are the different parts that we're going to be using. Eventually all of them, and I'm going to introduce all of them right now. Pressure, just like length, can be measured in a variety of different ways. We can measure temperature in atmospheres. We can measure them in millimeters of mercury. We can measure them in torr, and we can measure them in kilopascals. Which would be 101.325 kPa. And notice I used the values for them at standard. So this is standard pressure. So 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, and is equal to 101.325 kilopascal. We can use these conversion factors to figure out these answers. Volume, you will see milliliters and liters. For number of moles, that's N. You'll see moles. For temperature, you will see degrees Celsius and Kelvin. Now, we want to first be able to do the conversions. Celsius to Kelvin is one that we're familiar with. We just take Celsius and add 273 to it, and that gets us our Kelvin. Milliliters to liters, we have 1,000 milliliters is equal to 1 liter. And then moles is just moles. So these are the different units that you need to be familiar with and be able to convert back and forth appropriately. So the first one, we have millimeters of mercury, and we want it into atmospheres and into torrs. And so we set it up like this: 562 millimeters of mercury, and we just use factor label. We have 760 millimeters of mercury is 1 atmosphere. So I'm getting that from over here, right? So 1 atmosphere is equal to 760 milliliters of mercury. 1 atmosphere is equal to 760 millimeters of mercury. Those go away. We end up with an answer of 0.74 atmospheres. The millimeters of mercury and torr are the exact same unit with 2 different names, so that's going to be the same for torr. And then for kilopascals, we could do 562 millimeters of mercury we could say 760 millimeters of mercury is equal to 101.325 kilopascals. And that gets us 75-ish, 75 kilopascals, 74.89, something like that. All right. Number 15 here. Oh boy, there is a lot of stuff here. Let's see if we can organize it. Boyle's, Charles, and Avogadro's. And yeah, let's do it this way. We have Boyle's, Charles. Boy, I'm having problems writing today. And Avogadro's. All right, so Boyle's, as pressure goes up, volume goes down. The graph looks like this. And we have the relationship P1 V1 equals P2 V2. Charles, as temperature goes up, as temperature goes up, volume goes up. As temperature goes down, volume goes down. And so we have a graph that looks like this. Avogadro's law is going to be a little bit different. I'm going to come back to that one here shortly. Boyle's and Charles, though, we have one last thing, which is the indirect relationship here, or inverse relationship. One goes up, the other goes down, and this is going to be a direct relationship. One goes up, the other goes up. Now for Avogadro's law, this one is a little bit complicated, so let me put up a reaction here. We have, let's make sure I get this right. We have N2 plus H2 gets us NH3, and balance this thing here. We got 2 and 3. All right, so these are our mole ratios, right? And we have 1 mole to 3 moles to 2 moles. I was trying to get this guy's, there it is. I'm going to do top right. Sorry about that, guys. I'm just trying to get my tool out of the way. All right, there we go, got it. So we have mole ratios here. This also works for a molecule ratio, right? If we had 1 molecule of nitrogen, 3 molecules of hydrogen, and we'd get 2 molecules of the ammonia. That's because moles is a counting device, like dozens, and so it just works out that way. Now, for gases, it also works for liters. So if we were to have 1 liter of nitrogen, we would get 3 liters of hydrogen and 2 liters of ammonia. And that's because all gases behave the same and they're all completely miscible. And so regardless of what kind of gas we have, that will be true. And that's Avogadro's law. All right, that's a new one. This one is new. The other ones are reviews from before. Okay. Explain why a helium weather balloon expands as it rises in the atmosphere, and that is because as we go up the atmosphere, So we increase in altitude, the pressure, my goodness, pressure decreases. And as pressure decreases, the volume increases. So this is some information you would need for it to be able to do that. Incidentally, as you go down into water, the pressure increases. So some future information for you. Now we got some math problems to do. Let's plow through a few of them. First ones are Boyle's law, and then we get into Charles' law. We have a gas occupying a volume of 725 milliliters and that kind of a pressure. And we're going to look at a new pressure of 0.541 and figure out its final volume. So we can set this up. Again, here is P2, V2. And before I do this problem, I do want to show you something over here. We always have the same equation, P1 V1 over T1 is equal to P2 V2 over T2. And we can use this is the combined gas law. We can use this to figure out any kind of these problems where there's a change. So we have, right, a change that occurs. That's our clue to use this kind of as an equation. And then we just get rid of whatever is constant. And so the temperature is going to be constant, and so we can simply get rid of that, and we have the law that we need, and that's going to be Boyle's law. All right, now we can plug things in. Pressure of 0.970 and 725 milliliters. Notice, guys, I did not change the units on either of these. When we're dealing with a relationship like this, we just need to make sure that we keep the same units on both sides, and that's because of the metric system. All right, we have then 0.541 atmospheres on the other side, and then we can solve for our volume. Now, when we do it this way, that means that our answer has to be in the same unit as what we started with. So our answer is going to be in milliliters. We end up with a value of 1,300 milliliters. Number 20 is a little bit of a tricky one. We have a 46-degree sample of ammonia and has a pressure of 5.3 atmospheres. And we're going to change that volume to 1/10 in its in its volume. So it's 1/10 as large. So it looks like we have either like too much information or not enough information or whatever. But when we start looking at things, we can come up with some statements that will help us figure out how to answer this problem. The first one is that the temperature never changes. It gives us a temperature, but it doesn't matter because it doesn't change. It's 46 degrees before we do the change. It's 46 degrees after we do the change. And so that means that we get rid of it, and we're still left with Boyle's law. So that temperature is just there to make us think and use our problem-solving skills. We have a pressure at 5.3 and then a volume that isn't listed. But we do know that the secondary volume is 1/10 as large. So all we have to do is say that the initial volume is equal to 1, and the final volume is equal to 0.1. And once we have those two different values, now we have everything that we need. Here is my initial information, here is my final information, and plug things in. So 5.3 times 1 is equal to our pressure is what we're looking for, times 0.1. Do our math, and we end up with a value of 53 atmospheres. Look at that. All right, next one. All right, 21. The volume of the gas is 5.8 liters, measured at 1 atmosphere. What pressure is it going to be at 9.65 liters? Again, notice that we have units here to worry about. We have liters here, liters there, liters here, so that's fine. We have pressure here of atmosphere, but look, we need to have it into millimeters of mercury. So I'm going to take this, and I'm going to go ahead and convert that one into millimeters of mercury, because that's what my answer needs. So we have 1 atmosphere is equal to 760 milliliters of mercury. Plug things in. And we end up with a value of 465 millimeters of mercury. Now this is a trick that we do with Gen Chem students. I just want to remind you guys, not something that I expect you to do, but if you're struggling with these things, it might be helpful. And we just have this on the side. And organize your data. 5.8. Oops. I did something wrong here, guys. Let's see if I can figure things out real quick. The pressure is 1. The volume is 5.8. That means that the volume here, oh, that's fine, 9.65, and the pressure is 465. Now let's get this into milliliters of mercury, 760, and this is our answer. So we can do it this way and then set it up from there. All right. This one is another Boyle's Law problem. I think we've done enough of these here, so I'm just going to give the answers. A is equal to 0.69 liters. Boy, could my handwriting be any worse on this thing? Let me try that one more time, guys. 0.69 atmospheres, and B is going to be 60.8 atmospheres. And you can stop yelling at the screen. I hear you. This is not atmospheres. This is liters. All right, now we get into question number 23, which is the first one where we have a Charles Law problem. And then we can tell it's a Charles Law problem because we're dealing with a change in temperature. So let's bring this guy back. P1, V1, T1, P2, V2, T2. And now the temperature is going to change. We have a volume involved, but the pressure is going to be constant. And so we can go ahead and get rid of pressure. So there is our gas law. All right. Now the one thing about gas laws, and really any time we deal with temperature, that always has to be in Kelvin. If you leave it in Celsius, it will be wrong. No questions about it. So convert these into Kelvin, 298 Kelvin, and this one's going to be 361 Kelvin. Now we have those, we can plug things in. 36.4 liters. Put the label in there. Sometimes I do, sometimes I don't. I don't really care for these kind of problems. 298 Kelvin is equal to a new volume over 361 Kelvin. Now, just like you guys are familiar, you're going to be cross multiplying and dividing. We end up with the new volume equal to 44.1 liters. All right. If you would like more practice on those gas laws, including some more on, say, the other law we're going to look at, Gay-Lussac's, and the combined gas law, I can provide those for you. All right, learning objective 3, the ideal gas law. So we have standard temperature pressure and the significance of it and being able to use it. So STP is standard temperature pressure, and that is going to be a temperature equal to 0 degrees Celsius or 273 Kelvin. The pressure is 1 atmosphere. So those are them. Now, what is the significance related to the volume of 1 mole of gas? And that's the other part that we should say here. I guess the mole is equal to 1. And then the other part here is the volume. Now, this is something we do bring up in Gen Chem just briefly, and it probably just skips right past you. But if we have these conditions right here, all of those, and that's true, the volume of that gas is going to be 22.4 liters. That's always a true statement, ladies and gentlemen, and regardless of the gas that we have. And that's about the size of a basketball, I guess. So to give you a visual of what 22.4 liters look like. And so there you go. There's STP and then the volume part as well. Now, what's great here then is that we can use that information to be able to mathematically prove, this is a mistake, get rid of that, R. So if we look at the next part here, which is the ideal gas law, this is our friendly Pivnert. And so we have pressure, volume, number of moles, R constant, temperature. And we should take a little bit of time to go through all of those. And so maybe here we can do that as well as mathematically prove R. So pressure is equal to atmospheres. Volume must be in liters. N is our moles. R is our ideal gas law constant, which is 0.0821 liter atmospheres mole Kelvin. And we're going to come back to that guy here shortly. And then we have the temperature, which is equal to 273 Kelvin. Now, what the problem is asking us to do here is to mathematically prove that not only that R constant has that value, but also has that label and why that label is there, why it matters. And if we're at STP, we're looking at a pressure of 1 liters is 22.4, moles is 1, and temperature is the 273 Kelvin. And temperature has to be measured in Kelvin. So let's plug things in. PV equals nRT. Pressure is going to be 1. Volume is going to be 22.4. Number of moles is 1. R is what we're looking for. And temperature is 273. Now, I actually haven't put this into a calculator recently, but I'm going to assume that that value comes out to be 0.0821. Now let's do the exact same thing, but now let's look at the units instead. The units here are atmospheres and liters. That equals moles. R is the value we're trying to solve for, and then Kelvin. If we get R by itself, we're left with atmospheres and liters on the top, and mole and Kelvin on the bottom. So I hope you can see here now that we are not only identifying the value of this constant, but the label is important too, because if we were to change this to millimeters of mercury, this would get changed to 760, and that R constant would no longer equal 0.0821. It would be a different value because we're using different units. So that is a better explanation of what the R constant is and how it's obtained and why it's useful and why the label is important than what we cover in general chemistry. All right. Now we can do some ideal gas law problems. I'm probably not going to do all of these guys, maybe just 2 of them before I go on to the gas stoichiometry. Maybe I'll pick out a couple of them to do, and then we'll move on. I'll do the first one here, then I'll give some answers, maybe do some of the other ones a little bit more difficult later on, just so we can see what an easy one looks like so you're not fooling yourself, and then what some of the more difficult ones look like. Let's go back to orange. I like that. I do like setting these up this way, P, V, N, R, T. It helps organize things and keep our variables straight. Pressure is going to be 4.7 atmospheres, or volume 2.3 liters. Moles is what we're looking for. R is R. I'm not going to write down R probably ever again. Well, let's do it one more time. 0.0821, and we have the label there. But otherwise, I'm always just going to refer to it as R. Temperature in this case is going to be what is that? 305, 273 plus 32 gets us 305. You know what? I am going to switch out of this orange. I think maybe it might be too difficult to read. Let's go back to maybe red. We can plug things in. 4.7 times 2.3 equals N. Again, I'm just going to write R times 305. And N comes out to be 0.43 moles of nitrogen gas. Ooh, so this is a good one to bring up real quickly because you'll see a problem like this sometime else, I'm sure. Nitrogen gas is N2. It's a diatomic, and so that is how you would report it, as N2, not just N. All right. I'm going to give you a couple answers here. If something does, I do make small mistakes like this sometimes, ladies and gentlemen, so if something doesn't look right, please leave me a comment. I'll go back and check on it, and if I made a mistake, I'll correct it in the comment section. All right, so 32 is 6.2 atmospheres. 42 is 6.0 times 10 to the minus third atmospheres. And then number 90 we are going to do. All right. We have a gas at 27 degrees Celsius, 10 moles, and a 1.5 liter container exerting a pressure of 1.3 or 130 atmospheres. It says, is this an ideal gas? So if we use our organizational tool, this problem looks really confusing from the beginning because we have a pressure 130, we have a volume 1.5. It tells us the volume of the container, but remember, gases completely fill the container that they're in. So regardless of the size of the container, that's going to be the volume of the gas. The number of moles is 10. R is R. The temperature is going to be 300. And it looks like then there isn't a problem to do because we have all of the variables. This is an interesting style problem, but the other part of it is that, is this an ideal gas? There's a couple different ways that we can go about doing this. What I would like to do is to solve for, the volume and compare that volume to the 1.5. If the two values match, then it's an ideal gas. So go ahead and 130 times our volume, 10 moles, R is our R constant, 300 Kelvin. our volume turns out to be 1.9 liters. So this is not an ideal gas because 1.5 does not equal 1.9. So there must be some forces of attraction going on here, or repulsion, or something like that. Uh, 44 is an important one to do, so let's look at that guy. And then 45. We look at 45 just because of a mistake that's in there that I need to correct, but otherwise you can do that one. And 49, I'll do the challenge with you guys. That one's kind of fun. All right, so 44, we have a lot of different stuff going on because we're not given the correct pressure, we're given torr. We're also not given the correct moles, we're given mass. So we're going to have to convert those things. Oh, I apologize. I need to back up, ladies and gentlemen. I need to read the problem completely. It says, what is the molar mass of the gas? I knew that's what this problem was going to be because I wanted to do it with you guys, but I completely got off on my own thing, forgot. That's the important part though here. We get in torr. We're not given our correct pressure, so let's go ahead and change that. 741 divided by 760 gets us 0.975 atmospheres. So now we have that. Now the problem is asking for the molar mass of the gas. Now remember that molar mass is equal to grams per mole. We're given grams, 7.1. All we need to do then is to take that divided by the number of moles, and we can figure out the molecular mass. Some students have a difficult time understanding what this means. The grams per mole, you just divide and that gets you the answer. And yes, that's exactly the way it works. And it's similar to what we can talk about with speed. If I told you I was traveling 60 miles, I should say, 360 miles, and that took 6 hours, and I wanted to know my speed, so there's my data. Sorry, this is messy. I could figure that out by taking my miles per hour. I would take 360 divided by 6. Gets me 60 miles per hour. And since that's the exact same scenario we have here, grams per mole, if I have grams, I have moles, I can divide them, that gets me my grams per mole. All right, back to the problem here. I have 5.4 liters. The moles is what I'm looking for because that's what I'm going to plug into my molar mass equation here. R is R, and my temperature is going to be 44 degrees Celsius, 317 Kelvin. Do all the math to figure out the number of moles. We come up with a value of 0.202. Sorry guys, had to look that up. I hope you can read that. So 0.202 gets plugged in right there. And we can take our 7.1 grams, divide that by the moles, and we get an answer of 35.15 grams per mole. And there's our answer for that one. So it's one of those problems that seems like it's more difficult than it is. And once you start breaking it down, which is all what chemistry is, it turns out to be pretty straightforward. We just have to remember what the definition is of molecular mass. Okay, number 54. Again, I'm not going to do this problem, but I need to change some things. Remember these problems come from the textbook, and so I copy and paste these problems from a PDF version I have of the text, and it gets us this, 1.03 space 1023, which doesn't make any sense, first of all, and then also doesn't make any sense related to the problem. It says, okay, so maybe a scientific notation, right, is 1.03 times 10 to the 23rd atmospheres of ozone. It's not, it doesn't make any sense at all. So what this really is, and I'll spare the details, but it is 1.0 times 10 to the negative third atmospheres. So that is the value that goes there. Now you can do that problem and get an answer that makes sense, which is going to be, by the way, 2.93 times 10 to the 19th molecules. And I am extremely hopeful that you're going to be able to do that problem without my help. Now the challenge. A certain anesthetic, that's how you say that, yep, contains 64.9% carbon, 13.5% hydrogen, 21.6% oxygen by mass. And then we have values here: 100 degrees, 120 degrees Celsius, 750 milliliters of mercury, 1 liter of that stuff, and 2.3 grams. What is the molecular formula of the compound? So this pulls on some of the stuff that we did last semester, or last chapter, and that is the empirical formula. And remember that we can use the empirical formula to figure out the molecular formula if we know the molecular mass. If we know the molecular mass, then we can work that. Remember, the empirical formula is the lowest whole number mole ratio of the elements in that compound. And then the molecular formula is the true formula. So if the molecular mass is double what the empirical formula provides, then we have to multiply all of the elements, the ratio of the elements, times 2. And maybe once you get the problem up here, you'll be refreshed on how that works. All right, so the first thing we have to do is come up with the empirical formula. The second thing we have to do is figure out the molecular mass and then compare those two pieces of information. So we can go through here and figure out the carbon, 64.9 grams of carbon, 13.5 grams of hydrogen, and then 21.6 grams of oxygen. And here's 12 grams, 1 gram, 16 grams. Using some shorthand here to scoot by some of the work. That's all 1 mole. And we end up with 5.41 moles carbon, 13.5 moles hydrogen, and 1.35 moles oxygen. So that's the ratio. Now I have to get the whole number ratio. This comes out to be 1, 10, 4. So we end up with the empirical formula of C4H10O. And now we have to figure out if that matches the molecular mass. If we add all this together, we get a molecular mass of 74 grams per mole. And now for the molecular mass part, we go through and do some work with the ideal gas law. Pressure is going to be not 750, it's going to be 0.987. Volume is 1, the number of moles is what I'm looking for, R is R, and temperature is going to be 357. Now if we go through this, we have moles. Give me just a second, guys. I need to double check my math. Moles equal to, let's do this maybe in a different color, 0.00276. So take our mass, which is 2.3, divide it by our moles, 0.00276. And that's going to get us our, getting tired here, guys. That's why I'm messing up so much. That gets us our molar mass. So we're going to do 2.3 divided by that. Gets us 832. I feel like this is wrong. Let's find out. What's 832 divided by 74? 11. Oh boy. Let me go through this again real quick, guys, and figure out what's going on. There we go. The moles is wrong. There must have been some of the order of operations within my calculator. We end up with 0.0337. And we get a value of 68 grams per mole. Which does not quite match that there, but it's close enough. And so we're going to say that this is the molecular formula. I still feel like I did something wrong in that problem somewhere. I'm not sure exactly where that is. So if somebody points it out, I can fix it in the comments. All right. Now on to learning objective 4. Gas stoichiometry. So gas stoichiometry is just the same thing as other stoichiometry, where we have those same 3 questions. Is how do we get to moles? And then we go mole ratio. And then we figure out what our answer needs to be in. So 2 moles, mole ratio, out of moles. Maybe I can say that. And for this then, most of the time, you're going to need to use pivnert somewhere here. Either you're going to use pivnert to get into moles, or you're going to use pivnert to get out of moles. Now, there is certain times where you don't need to do that process, and this is an example of them, this one here. This is because of the Avogadro's law that we covered in Learning Objective 1, that the mole ratio is the same thing as a volume ratio. So this is the same thing as saying 2 liters of nitrogen monoxide to 1 liter of oxygen gas makes 2 liters of nitrogen dioxide. So if I have nitrogen monoxide, 9 liters of it, we would need 4.5 liters of oxygen gas, and that would produce 9 liters of nitrogen dioxide. So it is just simply the mole ratio. So a very easy kind of gas stoichiometry problem that students find really, really difficult because they forget about this once we start doing the more difficult, more challenging ones. The important thing here is that it has to be at constant temperature pressure. It doesn't have to be at STP, but that's a good clue. It just has to be constant temperature and pressure. All right. #52, we have methane here, and that's used in the combustion of heating units, whether you're going to be cooking with it or heating a home or something like that. And so now we have an actual kind of gas stoichiometry problem because we're starting off with CH4 and trying to end with carbon monoxide or carbon dioxide, how much carbon dioxide we're going to produce. Notice that this is a 1:1 ratio. And so we have our moles here to moles there. Since we have 15 moles of methane, we have 15 moles of carbon dioxide. So 1:1 ratio, 15 moles carbon dioxide. So I would go ahead and set this up. Then the other way, we have P, V, N, R, T. We have our moles 15. We have our volume. I lied, that's what we're looking for. We have our pressure. 0.985. We have the R constant. We have our temperature, which is going to be 296. And then we can solve for the volume, and that volume is going to be 370 liters. All right. Units, units, units. This one is all about the units because we're given kilograms here, and we're going to be asked to solve for it in milliliters. So very large measurement of a unit to very small measurement of a unit. So we're going to end up probably with a really, really large value. We're starting off with the solid. We're going to the gas. It's a 1:1 ratio again, and so we need to get to our moles, and since we're starting with our solid, we can just go to moles using our stoichiometry. So that's a comma, guys. There's 2,540. Oop, I need to get one of these out of here, don't I? And that is of sulfur, and then we can go 32 grams of sulfur as 1 mole of sulfur. There's my mole ratio, 1:1. I'm showing it this time rather than just explaining it with words. And then we can go through and calculate, and we get 79-ish moles. And now I can use Bivner. P-V-N-R-T. Moles, 79.4. R. Temperature is going to be 303.5. Volume is what we're looking for. And pressure is going to be 1.12. And when I did this, I got 1,766 liters, and that would be 1,766,000 milliliters. So there you go. All right. Glucose and ethanol. So ethanol is used in lots of different places. Ethanol is the primary component of, well, not the primary component, it is the alcohol that individuals over the age of 21 can consume. It's also the same kind of alcohol that is in gasoline, where it says 10% ethanol, so that's what it is. This is going to be very similar to the last one with one added little component, and that is the percent yield. Remember, the percent yield is the experimental over the theoretical. And the theoretical is what gets calculated by doing all of this work. I'm not going to go through this entire process here. We're going to take for this problem, we're going to take our glucose and convert that into moles of glucose. Then we're going to convert that into moles of carbon dioxide. And notice there's a 1 to 2 ratio here, and that gets us a value of 0.066 moles of carbon dioxide. Plug that into PivNert, and we end up with a volume of 1.62 liters. Anything you calculate is going to be the theoretical. This is what you should get. This is the 100% yield. This is the perfect score. So we're plugging that into the whole, the theoretical. So we take our 1.44, divide that by 1.62, and we get a value of 88.8%. All right. We're getting into something called Dalton's law of partial pressures here. And that's a new concept for us, but it's really simple. And all it says is that the total pressure, I'm going to do number 66 first. The total pressure is equal to the partial pressure. I'm just do 1. Plus the partial pressure of all of the different gases involved in that container, because all of the gases behave exactly the same. So if we look at number 66, we have a mixture of helium and neon gas that is collected over water at a temperature of here and at 745 milliliters of mercury. Now let's talk about this here briefly and see if we can make sense of what the problem is trying to confuse us with, basically. So when we collect water, gas over water, we are looking at a situation here where we have a container filled with water, and then we also have some kind of another measuring container up here with marks on it, and that is also filled with water. So this thing is all filled with water here. Now we have a hose that is connected to that container. And then this hose is connected to something else, whatever. In this case, it's a mixture of helium and neon gas, so it's probably connected to, I don't know, like a balloon or something here of those gases. And the gas then goes into the container so it can be measured, and as that gas bubbles into this container, the volume of the water decreases. And so we can measure how much gas it is by how much water that displaces. Now there's a problem with this. The problem is that we have 3 gases in this container. We have the neon here. We have the other one, neon and helium. Sorry, missed that one. Neon and helium in there. But we also have water vapor. Remember that water vapor is always there around us where we have water. It's humidity. And so we have to account for this water vapor, as this water vapor also exerts a pressure. It's a gas inside of the container with the other ones. And the reason why it exists is because we're measuring it over water. So this water here provides gas molecules into this measuring container that needs to be accounted for. So in this particular problem, we have three gases: helium, neon, and water. And it tells us the water pressure. And the important thing, this should be an equal sign, by the way, equals. The important thing to note here is that this vapor pressure changes based on what the temperature of the water is. Not the temperature of the air, but the temperature of the water. If we increase the temperature here, we increase the pressure of the water vapor, because there's going to be more water vapor in the container. Higher temperature, the more humid it's going to be. So in this case, we're looking for the partial pressure of neon. Sorry, this is getting kind of messy. So we can say the total pressure is 745 millimeters of mercury. We have an initial pressure of 368 for the helium. I'm just going to use helium here. We have then an initial pressure of 28.3 for the water, and we're looking for the pressure of the neon. And so we can just go through and do some subtracting here. We get the pressure of neon is equal to 348.7 millimeters of mercury. All right, so that's how you do a problem like that. Super easy once you get through all of the junk and you understand what the problem is asking you to do. All it is a sum of all of the different pieces. Now, number 63 is a little bit different. We're given a total pressure, but we're not given the individual pressures. We're given their moles. And so we could, if we're given like STP or things like that, we could figure out what the pressure is of each of these and do some calculations that way to figure it out and come up with the different parts using the same equation. But there's an easier way. If we can figure out the percentage of this gas that's methane, the percentage that's ethane, and the percentage that's propane, we can just take that percentage and multiply it by the total pressure. So if this is like 20% of the entire thing is methane, then 20% of the pressure is given to it by methane. So we can do this by taking the 0.31 moles of methane and divided by the total moles. The total moles in this case is going to be, maybe I don't have that, 0.85. Let me double check that, guys. Yep, 0.85. So if we get the percentage here, that comes out to be 0.365. So 36.5% of this gas is methane. So if we multiply this by 1.5 atmospheres, we end up with the partial pressure, which is going to be 0.547 atmospheres. You're going to do the exact same thing for the ethane and the exact same thing for the propane. You're going to take the two things divided by each other. In this case, it's 0.25, 0.29 divided by 0.85. And I don't have those numbers written down, but we end up with values here equal to 0.441 and then 0.51 atmospheres. Now, the reason why we put the Dalton's law of partial pressures in this gas stoichiometry section is that one of the ways that we can collect a volume of gas is using this method right down here. And so if we want to use that method to collect the volume and then use PivNert to be able to calculate moles or whatever, we have to be able to account for this vapor pressure of water. And in order to account for the vapor pressure of the water, we need Dalton's law of partial pressure. So that's why I put in this kind of stoichiometry section, and we're going to do a practice problem related to that, and that's number 67. All right, so let's look at this guy together and see if we can come up with some information. Again, this is a copy mistake. This one right here, this here, that should be an equal sign. All right. So we have a piece of sodium metal that reacts and does that equation. So we have sodium metal, which is the solid, and we have hydrogen gas, which is the gas. So we're probably going to be looking at sodium, or probably going to be looking at hydrogen, because water is going to be in excess, or that's going to be, in excess when we do the reaction, and then the sodium hydroxide is going to be aqueous, and that's going to be difficult to measure. All right, so the hydrogen gas is collected over water at 25 degrees Celsius. So that's that diagram I just drawn. And so I'm not going to draw it again, but that is the image that you need to get. We had the sodium being dropped into a beaker. That beaker was connected by hose and some kind of an apparatus to be put into that kind of a situation where it's being collected over water. And we have some information, how much of it is collected, and the pressure, and also then the temperature. So we have the temperature of what's going on here. Now we can assume that the temperature of the water is also going to be the same temperature as the gas. All right, so we are first going to use PivNert to get to moles of our hydrogen gas, because that's what we have information on, is hydrogen gas, and then go backwards to solve for the grams of sodium. So PVNRT. This is all about the hydrogen gas now. So the pressure, this is where we need to be careful. We have the pressure of 1 atmosphere, but 0.0313 of it is going to be of water vapor. So this is our total pressure, but our partial pressure is going to be made up of that hydrogen gas plus the partial pressure of the water vapor. So we need to subtract out that water vapor to get the partial pressure of the hydrogen, which is what we need to calculate. Remember that this ideal gas law is all for the hydrogen and only the hydrogen, not hydrogen plus water. So subtract out to get the pressure of the hydrogen, and we end up with 0.9687. The volume is 246 milliliters, or 246 liters. The moles is what we're looking for. R is R. Temperature is going to be 298 Kelvin. And our number of moles turns out to be 0.0097 moles of hydrogen gas. Now we can do our ratio. We have 1 mole of hydrogen gas to 2 moles of sodium. Now we can convert into mass. Cancel, equals 0.45 grams of sodium. And that is our answer. So again, account for the water pressure, the vapor pressure of the water, and then we're solving for our hydrogen gas first, and then we can solve for our mass of sodium. So remember, we're figuring out how can we get to moles based on the information that I'm given. How can I get to moles? how can I convert to the other thing? That's my mole ratio. And then what does my answer need to be in? In this case, it needs to be in mass. All right, click through to show you the last one. And for this one, I'm not going to do all of the work. I'm just going to show you again what you need to do in order to get this one. It's the exact same problem, guys. Just instead of using the sodium here and water, we're using zinc and hydrochloric acid. We still end up with the same products. We end up with an aqueous salt and then our hydrogen gas. We're given information about the hydrogen gas. That is going to be our 0.98 atmosphere, 7.8 liters, and 25 degrees Celsius. It's the figure 5.15, if you want to look that up in the book. That's going to be a better drawn picture of collecting gas over water. That's it. So we're going to use PivNert first. So PivNert gets us to the moles. Then we can use the mole ratio. And then we can convert into mass of the zinc. So PivNert gets us to moles, then our mole ratio, then our grams, and we end up with an answer of 19.8 grams of zinc. Wow, that seems like a lot. All right, but we can double check that and see if it's wrong. I can put that in the comments. Thank you, ladies and gentlemen. I hope this is helpful, and good luck.